Okay, so this thing is really similar to what we've just been doing, but we're talking about things that are now being hinged, okay? Things that are being hinged. Now, a hinge is something like this, like on a door, okay? You know, like a hinge at the edge of a door. And it means that something is fixed in place and it cannot move. It can only rotate at that particular point. So I'm going to talk about this diagram in a bit more detail. It tells us that this thing is hinged here, which kind of means it's like fixed, so it can't slide, but it's in that particular place, and all it can do is rotate upwards or downwards, right? When it's pushing into the hinge, it is also going to feel a reaction at the hinge. It's going to feel the hinge pushing back against it, okay? It is not going to feel the hinge pushing it across or up. It is going to feel a hinge pushing at some combination of across and up. So that's what I've written up here, that the reaction at the hinge will have a horizontal and a vertical component. So the horizontal component, we just use X because it's in that direction, and the vertical component we use is Y. The overall reaction will be a combination of X and Y. The overall reaction is probably going off in some kind of angle like this. This is actually the normal reaction that is at the hinge. And the normal reaction at the hinge, how do you think you can find out what R is if you know what X and Y are? Pythagoras, good. You can think about X going along, Y going up, and then there is the normal reaction. You can do Pythagoras to find out what R is, and if you wanted to find out the direction of that normal reaction, you could do SOHCAHTOA, okay? So I'm going to leave off this R force that I've got here, and I'm just going to proceed with the question. It kind of looks like the previous example. What would you say that the X force appears to be? It's like the friction, and the Y force is like the normal reaction. So it's the same kind of thing, it's just slightly different. There's a couple of things that might come up. Same things as before, resolve, resolve, take moments. So we've got a uniform rod of mass 5 kilograms and length 4 meters, has its end A smoothly hinged. That means there's no friction here, so we don't need to worry about that, at a fixed point. It's in equilibrium at an angle of 25 degrees, and it's being held there by a magnitude of force F newtons applied to the end, and it's acting in the vertical plane containing the rod and in a direction which makes an angle of 40 degrees with the rod. Everything is as though it is in the diagram. When it says a vertical plane, it means it's like this, and it's not wonky going to the side or anything, okay? First of all, we're going to try and find out what the value of F is. Well, actually, before I do that, I probably better add in my weights, and that this is 2 meters and this is 2 meters because it's a uniform rod. What do you think is going to be the best thing to do to find out the value of F? Good. I'm going to take moments about A because that will eliminate X and Y, and that's going to make things as simple as possible. So I'm going to start off by taking moments about A. Well, one of the forces is this 5G, and it's going to include this distance along the bottom. I could draw a separate triangle if I wanted to. I'm wondering if anybody can just tell me what that distance is. Yeah, 2 cos 25. That will save you a bit of time in the exam. So we've got 5G multiplied by 2 cos 25 equals this other force. Now, this other force is a bit trickier to find, so I may draw this one in. I'm going to draw the line of action of the force, and I want to find its perpendicular distance from this point. So it's going to be going from here. Oh, that's not very perpendicular, is it? It's going to be going from here up to here at a perpendicular bit. And we're looking for this green distance that I've got. So this is a triangle, I think. Actually, you know what? That might be useful for me to draw in. That's the 90 degrees. The hypotenuse is 4. And the angle of the triangle is 40. And I wanted that distance. Good. So it's 4 sine 40. And the force is F. So it's F multiplied by 4 sine 40. So F is equal to that divided by that. Believe it or not, that's 4 marks. Okay? This is why mechanics, it's so important about slowly doing this first line of working, because there's an awful lot of marks in there. So that's 5G times 2 cos 25 divided by 4 sine 40. And we get that F is 34.54413 blah, 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 which is just 34 point, whoops, can't even write properly. 34.5 newtons to 3 significant figures, okay? Can you see when I'm doing this, or am I completely in my own way? You can look there as well. Okay, do you want me to tilt this? You've got your own personal screen. Okay, now we're going to do part B, which says find the magnitude and direction of the vertical component of the force acting on the rod at A. Yeah, so it's asking us the vertical component of the force is Y. The magnitude is just the size. But the direction, what on earth are they talking about the direction of the vertical force? It sounds like they're telling me what the direction is by saying it's vertical. What do you think that means? No, because it's not asking me anything to do with R. It's just asking about this one here. Good. Negative or positive? Is the reaction force going upwards, or is the reaction force going downwards? Now, how on earth could the reaction force be going downwards? Just have a think about what's happening here. What could you tell me that might mean that the reaction force is going downwards? Yeah, it's being pulled up. If this F force was really, really big and you were like yanking it up from the floor, you would be pulling against the hinge, and so the hinge would be pulling downwards on it. The hinge would be tugging at the rod, okay? We're not sure what's going to happen. We've just predicted that it's going upwards, and if we get a negative answer, it actually means that it's going downwards. So that's all it's saying about direction. All it wants us to say is it up or is it down? So it should be pretty straightforward about what we're going to do here. We're going to obviously be resolving in the up and down direction because that's where we've got the Y value it is that we're looking for. So clearly I've got Y and I've got this 5G, but I need to think about this F. Now remember, you're only allowed to resolve up and down and left and right. So this F force here needs to be split into along and up. What's this angle here? So what's this angle here? 15. So the one going along is F cos 15, and the one going up is F sine 15, which tells me Y plus F sine 15 equals 5G. Y plus F sine 15 is equal to 5G. So Y is 5G minus F sine 15, and I've already got F stored in my calculator, so I can just find out what Y is equal to. So that's 5G minus the answer times by sine 15. You get that Y is 40.05, Y is 40.1 newtons to three significant figures. Okay, 0.593, blah, blah, blah. So it is 40.1 newtons, and it is acting vertically upwards, right? You may have seen, if you did watch this video, which I didn't ask everyone to, I added in a part C and I said, find the magnitude of the reaction at the hinge. So this one we just looked at the magnitude and direction of the vertical part. This is now asking for the overall reaction. So that means we're going to have to do the last thing that we haven't done, which is resolve left and right. So this made up part C question is if we resolve left and right, we go back up here. What do you think are the left and right forces? F cos 15 and X. So X is just F cos 15. And F is this thing here, 34.544 blah, 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 multiplied by cos 15. So that is 34.54413 times cos 15. X is 33.367. Now, it wanted the overall magnitude. We know that X is going across at 33.367. Y is going up at 40.0593. If we want to find out what the overall reaction force is, then we would just Pythagorize. So R would be equal to the square root of 33.367 squared plus 40.0593 squared, square rooted. Okay, so that's what the overall reaction would be. If they asked for the direction, you would find out what theta is, and you would say above the horizontal. So if they ever ask you to find the overall reaction, that's what you do. Yep.
So you know if you have a peg,
Yep.
then you assume that the normal at the peg is 90 degrees.
Correct.
Unless they say so, but in this one, you always have to make it like X and Y.
So yeah, so it's a bit different because the peg would usually be up here. This one down here, we always just call it X and Y because in theory, the reaction at this hinge, meaning it can't move at all, the reaction could be going like this, it could be going like this, it could be going like this, it could be going like this. Any of those reactions can consist of just two of them, a horizontal and a vertical. Because if you had a negative one for Y, it could correspond to this one down here. You've got something going to the right and something going down. If you had a negative one for X and a negative one for Y, it would correspond to this kind of thing. So all of the information will just kind of come out. We just usually put X and Y in that direction and let the positives or negatives tell us where the arrows were actually meant to be. So we've got enough time for me to do this last example to finish us up on this topic. Hang on a sec. And we're going to just zip it up there after we do that example. It's a pretty tricky one. And then it just means next lesson, we can spend half of the lesson either going through ones you couldn't do from homework, or we can do some like practice on the whiteboards for half of the lesson. And then the other half of the lesson, we move on to our final topic of mechanics, which is a complete breeze, okay? Like a complete breeze. It's further stuff with Suvat. It's just, but nothing like projectiles. It's just literally Suvat, but with vectors. It's just doing loads of topics we've already done, but just with vectors. It's very easy. Okay, this is an unpleasant question. So let's do it. This is one of the new specification questions. So this is the kind of like nasty thing they want to be able to do. So it's got lots of information for us to read through, but it's basically all in this diagram that we've got here, okay? It says a beam AB of mass 20 kilograms and length 3 meters is smoothly hinged to a vertical wall. So it's kind of being hinged into a wall like this. And what it goes on to say is the beam is held in equilibrium in a horizontal position by a rope of length 1 meter. One end of the rope is fixed to a point C on the wall, which is vertically above A, so the rope is being fixed from here, and it's then being attached to the point D on the beam so that the angle ACD is 30. So there's like a rope from this point of the beam that is attached to the wall up here, and that's stopping it kind of flopping downwards. It's keeping it in that horizontal position like that. So it's no longer hinged at the floor, it's being hinged at the wall instead, okay? I think the other bits we've got here, it just says the beam is modelled as uniform, the rope is light inextensible string, and we're going to find the tension in the rope, then the direction of the force exerted by the wall on the beam at A. There's a lot of marks here, and then we're going to do a couple of things to do with some modelling changes that happen at the end. So the reason this one is a little bit trickier is because they've just told us that the length of the rope is 1 meter and that this is 30. So let's see if we can just add in some of the forces to this diagram that I've got here. Luke, can you tell me some forces that I can add into this diagram? The reaction at the hinge, which I'm going to call X, and I'm going to call Y, because we don't know which direction they're going to be, left or right, or up or down, but we can say they're going to be a combo of those. Janet, another force I can add into this one? 20G, bang in the middle. Any other forces, anyone? The tension, yeah, there's going to be some tension. Now, which direction should the tension be going in? Towards C or towards D? Towards C, because we're imagining what is it like to be the beam. The beam feels like it's being pulled upwards in that kind of direction here, okay? So we need to do one of those three things, resolve, or take moments. Any suggestions? Take moments about A. Why is taking moments about A going to be the best? Because we don't know X and Y, so we can eliminate X and Y. So the best thing to do here is going to be to take moments about A. Well, thank goodness, we've got a really easy one to take moments about A here. 20G times 1.5, a flashback to 2 lessons ago when we were doing things like this and finding it difficult. Now look at this, okay? So we've got 20G multiplied by 1.5. Which is the other force that's going to be opposing that? Yeah, it's the T that we've got here. Now, there's 2 ways of thinking about this. If you watch the video, you'll have seen both of the ways of doing this. But the way that, if we're doing it with the non-physics way, the way that I've done it, we've got the line of action of the force, which is here. And we've got the point A, and we're looking for the perpendicular distance, which is here. Okay? But when I draw that triangle out, which I am going to draw out again here, 1 meter is not this side here. 1 meter is the entire piece of the string. So I don't even know the hypotenuse of this triangle yet. Could you work out what the hypotenuse of the triangle is, given that this is the big triangle where the hypotenuse is 1 of that triangle and this is 30, and this line here is the same as this line here? It's 1 cos 30. So this is cos 30. So this is kind of weird, right? The hypotenuse is cos 30, and we're looking for this distance here. So what would this distance be? Cos 30 sine 30. The hypotenuse is cos 30, and it's the opposite of the sine 30. We don't have to worry about that because we can just put it in a calculator. But yeah, we could combine it with a double angle. So this distance here is the hypotenuse, which is cos 30, multiplied by sine 30 because that's the angle. So the distance is cos 30 sine 30, and the force is the tension, which is T cos 30 sine 30. The other way that we could have done that, and I'm just going to do a quick sketch of this. That's 1, that's 30, and this is T, is you could have resolved the T into an upward force and an acrossward force. The one going upwards would have been T cos 30, and the distance that it would be away from the point A is the bottom part of that triangle, which is the bottom part of this triangle, which is sine 30. So you have T cos 30 multiplied by sine 30, T cos 30 multiplied by sine 30. So you can either do the splitting of the force or you can do the distance, okay? Both challenging. I think they are both confusing and different to things we've seen before, which is why it's excellent I'm showing you this, because I don't want you to be scared when you see things that are a bit different. Okay, great. I'm just going to solve that equation now and find out what the tension is. So the tension is just going to be that divided by that. And it's good to see some other people are doing this on the calculators as well, so that if I've done it wrong. Yeah. Yeah. The distance here becomes sine 30, not T sine 30. This distance is sine 30 from this triangle, and the force is T cos 30. This force here, which is T sine 30, is going in this, is got a distance of 0 from the point, so that force doesn't even get included. That's the physics way of doing it. Yeah? What's the question you've got in your head? No, because we can't mix together forces and distances. They're like separate from each other. What did you get when you typed that in, Janet? 678. Good, 678.9639, blah, blah, blah. So 679 newtons to 3 significant figures. I've used this one just in case I need it later on. Now it wants the direction of the force exerted by the wall on the beam at A. So that sounds like we need to do something to do with x and y and then find out what theta is by doing the inverse cos. So this was part A of the question. Part B of the question, I'm going to resolve left and right. Left and right, I can see that x is going to be equal to, well, I need to split this T force into a force going up and a force going across. If that's 30, that's T cos 30. And that's T sine 30. So what does it look like x is equal to? Good, T sine 30. And we know that sine 30 is just a half, so I'm just going to half that. And we get that x is 339.4819, blah, blah, blah. Then I'm going to resolve up and down. What does it look like the up and down calculation is? Y plus T cos 30 is equal to 20g. So, whoops, y is equal to 20g minus T cos 30. And I'm going to just use the values that I've got already. So I'm going to do that times that, and I'll do that, take away that. And we get the answer that y is minus 392. I'm pleased this happened. It means it's going down. I wanted to show you this happening. So it's not actually going up. The reaction is going down, and that's because the rope is pulling it up with such force that it's actually tugging against the reaction. It's not resting on the hinge. It's actually pulling against the hinge instead. So we now want to find out what that angle is. Well, the X force is 339.4819, and it's going down 392. So we're looking for the angle that they have here. So theta is the inverse tan of the opposite, which is 392, over the adjacent, which is 339.4819. So that is 392 divided by 339.4819 inverse tan, and we get that the angle is 49.1 degrees below the horizontal. Hamza, it's a bit distracting. Okay, you can either whisper really quietly, but it's just a bit distracting. And if you wanted to find out the magnitude, Pythagoras. Okay? Now, here comes some interesting stuff. It says, if the rope were not modelled as being light, state how this would affect the tension in the rope, explaining your answer carefully. Noting it's 2 marks, you can't just say one thing, you've got to say 2 things. If anybody's watched this or remembers this, what did I say about ropes not being modelled as light? Yep, so they have mass, but how would that affect the tension?
Would it be different at different points?
Good, the tension would be different at different points. That's one of the marks. The second mark is to explain a bit more carefully. So think about if this rope here wasn't a really thin, light piece of string, imagine it was a really, really heavy rope that had maybe, I don't know, a mass of like 10 kilograms. Pardon? There wouldn't be a normal contact force, but if you imagine a really thick, heavy rope, the bottom of the rope is just having to support the beam, the top of the rope is having to support the beam and the rest of the rope. So if you're at the top of the rope, you're having to imagine being now a part of a string. If you imagine being the top part of the string, you're also having to support the whole bottom of the string as well. So what we would say is not being modelled as light, this would affect the tension in the rope. We would say if not light, the tension would not be equal throughout, and would be greater at the top. I'm going to have to go down here. This is because it needs to support its own weight. It needs to support its own weight that's at the top. So that's why it's a 2-mark question. You can't just say one thing for that one. We're nearly there. The rope is now moved and replaced by a longer rope, which is still attached to the wall at C, but it's now attached to the beam at G, where G is the midpoint of AB. So the rope is going to change from here to here. It's going to change from here to here. The beam AB remains in equilibrium in a horizontal position. Show that the force exerted by the wall on the beam at A now acts horizontally. So the force that is acting on the beam at A is only going to be acting horizontally. In other words, there's only going to be X. The Y should be disappearing completely. So I'm going to redraw the diagram because I can't cope with doing that same diagram again. We've got the 20G that is here, and this point in the bit here is G, and it says from C, that's a terrible drawing, from G to C, we've got the tension. This is A, this is B. We know that there's still a reaction here of X, and we know that there's still a reaction here of Y, but we're hoping that Y is going to be equal to 0. I think that's all of the forces that we've got there. This is for part D of the question, right? Now, when I look at this, I go, oh, are we going to have to do the whole question again to show that Y is equal to 0? But it's only 2 marks, okay? So if you find yourself doing the whole question again, you're probably not even going to get one of those 2 marks because there's only 2 things that they're looking for, the correct answer and the correct method. So if you don't know how to do it, move on and do something else. Or say to yourself, okay, it's only 2 marks. That must mean it's something really straightforward with a straightforward conclusion. Can anybody spot what that straightforward thing might be?
Is it y equals 0?
It's not to do with y cos 90 being equal to 0, because we need to actually like show that this is equal to 0. We don't know that it is equal to 0. We're hoping that it is, just to show that there's a horizontal one. It's to do with moments and a particular place that you can take moments that would tell you that. Yeah, if you take moments about G, something interesting will happen. G is so called because it's the center of gravity. But if you take moments about this point, I want to think about what will happen to all of these forces. What would the moment be of T about G? 0. Why? Yeah, so actually the line of action of this force is going through G. So the perpendicular distance of T to G is 0. What other ones are going to do that? The 20G is also going through G, so it will also have a 0 moment. Which else has a 0 moment? X is also going through G, so we'd have a 0 moment. So the only thing that we need to do when we're taking moments about G is we just need to take moments with the Y force. Now this distance is 1.5 meters and it's already perpendicular, so we just get the perpendicular distance multiplied by the force is equal to, well, there's nothing else doing it, so it's got to be equal to 0. Which means y is equal to 0, hence reaction acts horizontally. This is why it's a 2-mark question. 1 mark, 2 marks. Yeah, you can divide 0 by 5. 0 divided by 5 is 0. No, that's 5 divided by 0. Okay? Hard question. This is, seriously, this is the hardest stuff that I think you can do in applied maths. I think it's harder than the stuff that there is in stats. I think that you all will, by the end of stats, I think you will all be saying stats is easier than mechanics. I hope that you've enjoyed mechanics, but this is the hardest stuff that there is. If you've enjoyed this, then that's great. That's really, really good.